around the 20th of August. So it's normally associated with the Hartwig and Ward are normally given the credit for discovering this supernova. It's not clear which one was first, but it could have been Isaac Ward. However, the next one from Ireland, so this one was discovered from Ireland, a supernova discovered from Ireland in 1885. The next one discovered from Ireland was in 2010. So we had to wait another 125 years to discover a supernova from Ireland. Probably because we had to wait another 125 years for a clear night. But
我刚刚忘了讲说，中子星是一种，等一下可能会讲到，就是非常非常密的一种，它整个星球就是由原子核的那种密度组成的。当时司马教授说，把全世界的人全部都压到一个像汤匙这么样大小的话，那个的密度就是中子星的密度。这边当然还是讲一个这个 ，by the way， 这个 nova 这个字啊，它有 supernova， 这个 nova 这个字是拉丁文，就是 new， 就是英文的那个新的意思了啊。不是光是卖电脑的那个电那个厂商而已。但所以 nova 就是新的星球，因为以前的人以为是刚刚出现的 ，supernova 就是超新的，特别新的，比 nova 还要更亮。这边是讲说，在那个爱尔兰，他们在19世纪的时候看到了在不是我们银河系，是我们邻近的银河系里面的超新星的爆发。可是这两个过了以后，过了100多年以后。在都柏林，在那个爱尔兰的首都啊，2010年的时候才又发现了下一个超新星。他开玩笑是因为他说要等120几年才在他的国家发现了下一个，是因为可能120几年他们才有一个晴朗的夜晚，让他们可以发现。爱尔兰的天气跟我们北台湾的天气很像，一天到晚都是阴天啊。even translate 也有。
So a new star was discovered in Andromeda, and it was called a nova. But does anyone know the fundamental measurement to make to try and determine how bright an object it really is, the luminosity of an object? If you see a bright star here, or anywhere in the sky, what's the fundamental measurement you would make to try and work out how luminous the star is, and really how bright it is?
有人知道怎么样量一颗星球实际上有多亮？看起来这么亮，实际上有多亮？怎么量 ？Anyone？
Say it again. So, I think the answer is the distance, right? Yeah, exactly. Measurement of the distance. Because if it's very close, it might be intrinsically faint, but if it's really far away, then you know that it must be very luminous. So measuring the distance to stars and galaxies is very important for understanding really how bright they are. So how luminous was this? Well, in 1920, there was a debate, the Shapley-Curtis debate in the 1920s about what we saw as galaxies. Were they nebulae in our own galaxies, or were they actually distant galaxies like our own, which they called island universes? Now, if you move a light bulb away from you, it gets fainter. If you move it closer to you by a factor of 2, the object becomes 4 times brighter. So objects get fainter by the square of their distance. So if you measure the distance, you can measure how bright objects are. And that's the fundamental measurement we must make for supernovae. And it's a fundamental measurement that was made to define the class of supernovae.
对，刚刚回答是很棒，还是对的，就是要知道距离。你一个东西看起来这么亮，你要知道它的距离，你才知道它实际上有多亮。一个天体或一个灯泡，它发出来的光啊，随时随地就发出 去了以后，它分布到一个球面上，所以东西就变得比较薄，就好像你把巧克力铺在那个吐司上面，你铺的面积越大，就越薄，光分的就比较薄。那这个球面的面积是根据你的平方乘反比啊，所以亮度就会根据你的平方乘反比。比方刚刚讲，如果你把一个灯泡拉近了一半，那么它的亮度就会有4倍的亮度，对吧？所以你知道的距离跟看到的比较，你就可以知道 intrinsic， 你可以知道内在的它到底有多亮。
Does anyone know who this is?
这是谁啊？
It's Edwin Hubble. So he did a very important measurement. So when the nova in 1885 was discovered, no one realized it was a supernova. They just labeled it a nova because they didn't know the distance to the galaxy. And the debate was still engaging, even in 1920, about the distance to these galaxies. Hubble then measured the distance to galaxies. And then Fritz Zwicky and Walter Baade, they were the ones that realized, wow, if Hubble is right, and this galaxy is very far away, and his distances are correct, then this nova must be unlike anything else in our own galaxy. It must be 2 billion times more luminous than the sun, and 10,000 times more luminous than the brightest stars in our galaxy, and the small novae that we see in our galaxy, these variable stars that do get bright, but they don't get as bright as supernovae. They realized this was the energy coming out of this nova was much more luminous. And this is when they coined the term supernova, or Chao-Xin-Qi. So I learned that this means new star, and this means great new star. Is that right? Am I right? Chao-Xin-Qi. Which is a great name. I think we should all use Chao-Xin-Qi for supernova and forget about using supernova. So these guys took the measurement of Hubble and then named this a supernova because of its total luminosity. So this is when, in the 1930s, this is when the study of supernovae really started.
1920年代到现在还不到100年之前，人们都还不知道宇宙的结构。当时在天空中看到的一个一个、一块一块的云，现在我们叫星云的东西，当年都不知道是在我们银河系里面，还是另外一个宇宙。它前面有一个字叫岛宇宙，当时有一个名字叫岛宇宙，认为宇宙中间一个岛一个岛一个岛。当时1920年还在辩论到底是什么样的结果，现在我们都懂了，都知道我们这个情形。那敲定这件事情的就是哈勃，他用了一些别的方法，测到了在仙女座星系，刚才那个星系里面的一个超新星的爆发，他测到仙女座星系的距离，看起来不相关的科学，对不对？我测它的距离，可是那个星球爆发了以后，如果它是在我们自己银河系里面，它就不需要特别亮。可是如果哈勃是对的，这个星系是很远很远的另外一个东西，离我们很远，那么这个爆发的当时爆发的星球，一定是要比一般的还要来的亮，所以才出现了超新星的这一个字。
So now we can discover supernovae in other galaxies, some quite nearby, some far, some more distant. So these are some images of galaxies. And many amateur astronomers, this is Tom Bowles from England, many amateur astronomers discover supernovae, even with small telescopes, which are 20 centimeter to 50 centimeter telescopes in observatories in some people's back gardens and backyards. These can actually discover supernovae nearby the Earth. So here's a supernova, or a new star in this galaxy. This is a supernova in the famous galaxy M51. There are some professional searches. So this professional search is based in California. But this one, and this that discovered this supernova, this one was discovered by an amateur astronomer called Wolfgang Kohler from Germany. And there's a famous Japanese astronomer called Koichi Itagaki who has discovered many supernovae from his small observatory at home. And these amateur astronomers play a major role in finding supernovae near the Earth. To find supernovae, you need to look at a lot of galaxies. For every galaxy has a supernova roughly once every 100 years. So if you want to find a supernova, you need to look for 100 galaxies for 1 year, every now, or more than 100 galaxies. The more galaxies you look at, the bigger the chance is that you find a supernova. And many amateur astronomers have been very successful in looking at many galaxies and spending many nights looking at images before and after and trying to find a new star that appears in these galaxies and have made a major contribution to science.
一个很重要的数字啊，就是现在就看了很多的星系以后，大概平均一个星系啊，100年左右会出现一个超新星。那我们的银河系已经过期很久了。那有一种可能就是它在银河系的别的地方，我们看不到。总而言之，就是我们的银河系已经很久没有超新星。那刚才 Smart 教授讲说，在发现超新星的这件事情啊，你要看别的星系。那你一个晚上你要看很多很多的星系。那如果平均100年一个星系才发生一个的话，那意思就是说，你如果看1年，你要看100个星系，对吧？平均1年可能会看到1年一个。所以你如果看到比较多，像刚刚讲的一些在美国的专门职业的望远镜、职业的一个专业的天文云台，或者是业余的，即使是很小的望远镜，可是他每天晚上可以看很多，去监测这些星系，他看看上一次的照片跟这一次的有什么不一样，就会发现是有星星亮出来的。业余的天文学家在超新星的观测方面做了非常非常多的贡献。
So what we know about supernovae, we know they appear. Zwicky and Bada made a proposal that they came from massive stars, and they came from the collapse of very massive stars and the energy that's enclosed in those massive stars, the gravitational potential energy. But we know that type 1a supernovae, we label these supernovae, the supernovae that come from what we call elliptical galaxies. And elliptical galaxies have only got old stars. They don't have any young stars. They don't have any massive stars. All the massive stars died out long ago in these elliptical galaxies. We call them red and dead. They appear to have old stars, but no new ones. There's another type of supernovae called type 2 supernovae that appear in galaxies like this that have got lots of stars, young stars forming, massive stars forming. So these supernovae appear in these galaxies. And type 1a supernovae appear sometimes in these galaxies, but they appear a lot in these old galaxies. So this is telling us that there are different origins for the different types of supernovae. Type 2 supernovae probably come from young stars, stars born in clusters, stars more massive than about 10 times the mass of the Sun. And these supernovae come from older stars. These are the ones that were used to explore the expanding universe because they all look quite similar, whereas these supernovae look very different. And this is probably because they come from many different types of massive stars, but these ones come from white dwarf stars. This is the type of supernova that Tycho found in our own galaxy. And this is the major piece of evidence that we have to tell us what type of stars produce these two different types of supernovae.
This is a complex slide, so let me explain more. We can have a drink.
Okay.
我稍微多解释一下，因为这张投影片背景知识非常的多啊。超新星啊，大致分2种，这起码今天只会讲2种，还有很多细的分。不过主要就是 1A 用罗马数字的1啊，就 1A 跟罗马数字的2。什么教授告诉我们说，他们分这2种呢，就第一种，它只在椭圆星系里面发现 1A 的超新星。椭圆星系里面是什么？就好像你今天如果要知道一个人某一种病，或者是某一种生活习惯，你去养老院看那边负责人，跟到幼稚园去看，你要做这2种比较的话，可以归纳出这个病是因为年纪啦，还是怎么样，可以归纳出来，对吧？那椭圆星系呢，它都是由很老的恒星做的，这星系已经很老了， 它连恒星都已经，因为恒星在演化的时候啊，大质量的恒星先死亡，然后中质量，然后再小质量。大家一起生下来以后，大质量、中质量都死亡，只剩下活得很久的，就是比较小质量。椭圆星系就是像这样子的星系。另外一种呢是在它星系里面还有很多恒星还正在做，所以它有很多年轻的恒星，包括了大质量的恒星都还活着的，它都是Type 2的超新星。那史马尔教授说 ，Type 2超新星呢，就是大质量它死亡的时候表现出来的现象。那 Type 1A 呢是白矮星，它因为有别的性质，等下会讲，让它每个看起来都比较像。都很类似，什么东西类似先不讲，就是每个东西都它很多性质都很像，所以就这两个星系你看起来就不一样。左边那个星系就是一堆只有恒星，没什么气体了，右边还有很多气体啊、尘埃啊，还有刚刚诞生出来的。
And this is just a color picture of an elliptical galaxy. That's a black and white one. And that's just a color picture of an elliptical galaxy that we see Type 1A supernovae in. So if we have a star, so I'm going to talk about Type 2 supernovae from massive stars. I won't talk about these anymore. These are a different type of supernovae. So I will only talk about the origins of Type 2 supernovae, which produce all of the oxygen that we have on Earth, the oxygen that we breathe, the oxygen in the water on the Earth. So for a star is a ball of gas which is trying to collapse under gravity. So what is the reason why a star does not completely collapse under gravity? What keeps it up? What's the physical reason that a star is spherical? It's huge. It's a million times more massive than the Earth. This is a picture of the sun. Why does it not completely collapse under its own gravity? What keeps it up?
恒星是一团气体，像太阳的话，它是地球的100万倍了。这么大的一团气体，有很大的万有引力啊。为什么太阳没有滑下去？
Nuclear reactions in the core, and what do they produce? Energy. And what type of energy? Heat. Exactly. And with heat, you get pressure. So in the core of the star, in the sun, and the core of any star, we burn hydrogen to helium through nuclear reactions. We have gravity trying to contract the star, or we have pressure. Heat pressure in the core, which keeps the star up. And through all of its life, most of the life of a star, gravity exactly equals pressure. So the star is very stable, it's very round. You look at a picture of the sun, it's spherical, almost perfectly spherical. So gravity must exactly balance pressure during the whole of the star's life. So now can you think of what might happen if you turn that pressure off? If you used up all of the nuclear fuel in the center of the star, what might happen?
好，刚刚回答的很好啊，就是恒星有核反应，核反应产生热，热就有压力，压力就推开了这个气体，所以热压力跟万有引力达到平衡。那现在的问题就是说，如果核反应没有了，进行结束了，那会发生什么样的事情？
Star will get smaller and the heat will raise up until react the next nuclear.
Very good, very good. So when hydrogen is used up, so hydrogen burns to helium. So for most of the time during the star's life, pressure equals gravity, the star is stable. At 15 million degrees in the center of the star, you can get fusion. We get hydrogen that burns to helium. 4 atoms of hydrogen and 4 protons gives us helium, plus energy, and that energy is the heat energy, which keeps the star up. Where does the energy come from? the mass of 4 hydrogen atoms is greater than the mass of 1 helium nucleus. And Einstein's famous equation of energy equals mass times the speed of light squared. So if the mass of 4 hydrogen atoms is greater than the mass of 1 helium atom, this extra mass is converted to energy. And this is what stars do. And the reason you can get so much energy out is that C is such a large number. Anyone know the value of C in meters per second? Yes? It's the speed of light. Do you know what the number is? How many zeros? Three and 6 zeros, but in which unit? Exactly. So 3 times 5 zeros if it's kilometers per second, or 3 times 10 to the 8 for meters per second. Okay? So it's a big number. So even if you have a small amount of mass, you take 3 with 8 zeros, and then you square it, multiply it by the mass. So you get a lot of energy out. So if you can convert a small amount of mass to energy, you can potentially create a lot of energy. And this is what stars do all during their life. Is that okay? And to give you an idea about the amount of energy, so this is a bag of sugar. You like sugar in Taiwan? 1 kilogram, if you look at on the side of the package, 1 kilogram will give you 17,000 kilojoules of energy that your body can use. Your body uses 17,000 kilojoules, but that's just chemical energy, of course. That's stripping off the electrons. That's changing the atomic structure of sugar. It's splitting the atoms up. It's not nuclear energy. Your body doesn't use nuclear energy. It uses atomic energy. So a little teaspoon is 100 kilojoules. 1 granule would be 10 kilojoules. Okay, so a sugar molecule is 12 carbon atoms, 22 hydrogen, 11 oxygen. Now, if you could completely destroy 1 granule of sugar, completely convert it to energy, not chemical energy that your body uses, but if you could completely destroy it and use Einstein's relation for energy equals mass times the speed of light squared, if we could completely convert 1 granule of sugar, we could get about 10 billion joules. That's how much energy there is in mass. If you can convert it, if you can raise it to high enough temperatures that you can actually destroy the mass and create energy. So mass has a huge potential to give you energy if you raise it to high enough temperatures.
很有意思了啊！这个 Smart 教授一开始说就是糖嘛啊，他说台湾很喜欢糖，因为我们有一次吃饭的时候，我们在开玩笑说台湾做菜很喜欢放糖，所以我们连肉里面都有糖。欧洲国家的人不习惯，他觉得肉不应该有糖，我们什么都放糖，炒菜也放糖，煮肉也放糖。然后有一个外国客人就讲了一句话说：“对，你们菜什么菜都放糖。” 只有甜点糖放的太少，这跟国外完全相反。我很喜欢糖。Anyway， 他说啊，这个糖啊，你把它换算回来，你看那个包装上面写它的糖的热量，发现一个糖啊，大概是10个焦耳，一克大概是10个焦耳，吃1克的糖可以获得这么多，可以换成卡路里啊。那么但是你如果用1等于 mc 平方，如果你能够把这个东西温度让它变高，让它原子核跟原子核反应的话，你就可以从它产生的新的原子核啊，质量少掉一点点，那个少掉一点点的质量，乘上一个光速的平方，就会变成一个很大的数字。有名的爱因斯坦这个公式是这个意思，所以他说那样子的糖，我们吃下去化学能只能达到10焦耳。 可是你如果变成核子能的话，它有10后面跟了1后面跟了10个0，这么多焦耳，核子能非常有效率。
So, as you said before, so when hydrogen burns to helium, creates this energy, this nuclear energy from hydrogen. When the hydrogen is used up, the core shrinks, the temperature goes up, and we can burn helium. And so helium can burn to carbon and also give us energy, because 3 helium nuclei are greater in mass than 1 carbon-12 nucleus. So this is the same process. It's just that we need a higher temperature, 100 million degrees, not 15 million, but 100 million degrees to burn helium to give carbon. When the helium is used up, carbon can burn, and it can burn the oxygen, magnesium, and sodium, for example. So this is the creation of the chemical elements that we see in the Earth, in the solar system, and in our galaxy. These were all made in previous generations of stars. The carbon, the oxygen, the magnesium, sodium, the silicon, and the rocks on the Earth were all made in generations of stars. After carbon is used up, the core temperature goes up to 1 billion degrees. Oxygen burns to sulfur, silicon, phosphorus, and finally, silicon will burn to iron. That's the final stages which will happen in a massive star. This will not happen in the Sun. The Sun will stop here because it's not massive enough to create high enough temperature to burn carbon, to oxygen, to magnesium, and sodium. So the Sun stops about here, but very massive stars, which are more than 10 times more massive than the Sun, have much more gravity. The temperatures can be higher, and they can burn their core all the way. The very center of the star becomes completely made of iron.
太阳啊，它的表面只有大概5000多度啊，但是它的中心啊可以达到1500万度。在这么高的温度之下，大家知道氢的原子核就是质子，质子跟质子呢，很快的速度的话，它可以接近，就会结合。4个这样子的过程啊，一系列的过程，4个氢换成1个氦，就获得了支撑了太阳的能量，1000多万度。但是到了，所以它的核燃料是氢，核废料是氦。可是如果温度再高，到了1亿度的时候，它就可以用4个氦的原子核，对不起，氦的原子核跟氦的原子核也可以产生反应，要3个氦变成1个碳12，一个碳12的质量也是小于3个氦的原子核，所以也会获得能量。这个过程可以一直不断的继续。如果烧完了说下去，温度上升就点燃下一级的核子反应。可是呢，太阳的那个外围引力不够强，它最后说下去温度不会太高。大质量的恒星 （massive star）， 它大质量的恒星大概10倍太阳左右这样的质量的恒星呢，它说下去温度就可以非常高，到达5亿度的时候呢，碳就可以结合成核融合成为氧啊、镁啊、钠啊这些东西。到了1亿度的时候，对不起，10亿度。到10亿度的时候呢，那个氧啊还可以再继续结合成硫啊、硒啊，还有这个磷啊这些东西。最后的化学核融合就是 silicon， 就是硒变成铁的，变成 iron。铁之后的东西就它的原子核的性质不一样，你再加东西进去呢，它不但不会缩下，它会放松，所以不能靠核融合，要靠核分裂。所以我们台湾各个地方用的核能厂都是用比铁还要复杂的东西。所以你我身上的这些元素全部都是恒星做的。所以前面那张标题，马尔教授写的，恒星就是核子反应工厂，它产生了很多原子核。
So right at the end of its life, when a star has a core made of iron, the structure of the star, we think, is like this. A massive star, and right in the middle, we have an iron core, which is surrounded by silicon, and oxygen, and carbon, and helium, and eventually hydrogen. Most of the star is still made of hydrogen, but the very center is made of the heavy elements that have been burned in the nuclear reactions in the star. If if you look at stars on what we call a Hertzman-Russell diagram, so this is what we think the star is like at the end of its life. If we look at stars in the sky, we plot temperature. So this is the temperature at the surface of a star versus the